All right, students, welcome to your AP question walkthrough on rate determining step and multi-step mechanisms. So we're going to finish out question 18 for our conceptual, and then we're going to move on to a short FRQ. So question one, part 1 and 2, we've already answered based off of the two-step mechanism. Now we're being asked for part 3 in question 18. What is the rate determining step, or RDS? So the rate determining step for a multi-step reaction is the slowest step. So for us, it's going to be step 1 is our rate determining step. How did we know that? Well, it's almost always labeled as slow, okay? So what is the order of the reactant, not an intermediate and not a catalyst in the RDS? So when we look at the rate law, okay, we know that the rate law of the overall reaction is going to equal the rate law of the elementary slow step, or the rate determining step. So we say that the rate law is equal to some constant K, or that's specific to the reaction, times the reactants of the RDS. And here we see that our reactant for step 1 is O3. Now, you might be tempted to write NO, right? Because that's also a reactant in step 1. But what you'll notice is that NO is consumed and then regenerated in the next step. So what we actually realize is that NO is a catalyst. So because of that, we would not write NO since it's a catalyst, and we would say that the rate law of the overall reaction based on the slow step, because it's kind of like the gatekeeping step in terms of how fast that mechanism can go, usually due to a high activation energy or a really complex collision requirement, is determined by the single reactant O3 that is part of the overall reaction. Okay, that is part of the overall reaction. And in elementary steps, we say that the coefficient in front is the reactant order. So this would have a reactant order of 1, which you can or often don't write. All right, so we say that this is a first order. All right, so finally, write the rate law for the reaction with respect to O3. And I actually kind of just did that. So I kind of comboed all of this. And so what you can do is you can translate it down to here. Rate law for the overall reaction being determined by the rate determining step is O3 raised to the power of 1, or just not written. All right. So let's move down to AP problem number 7, short FRQ, which again should take about 9 minutes and is allotted 4 points on the AP. And I went too far. Okay, so what we have here is, for this one, we are told that nitrogen dioxide, NO2, is produced as a byproduct of the combustion of fossil fuels in internal combustion engines. At elevated temperatures, NO2 decomposes according to the equation below. 2NO2 gas goes and forms or produces 2NO gas and 1 O2 diatomic gas molecule. The concentration of the samples are monitored, of NO2 sample is monitored as it decomposes, and it's recorded on the graphs below. The 2 graphs that follow it are derived from the original data, so they're derivations. So what you see here is you have NO2. Okay, you should immediately start looking at the Y and the X. We have NO2, concentration of the reactant. We have 1 over NO2 and ln over NO2. So immediately you should know this is an integrated rate law question. Integrated rate law question, hence the word derived. So when we have NO2 in time, we know that this is going to be 0 order. When we have 1 over NO2, we know that this is going to be second order. And when we have ln NO2, we know it's going to be a first order, okay, relationship. Now, what we look for is, when graphically speaking, we look for the relationship between time and concentration, or the derivation of concentration that gives us a linear. We are looking for a linear relationship because that will reveal to us the order. All right. So for us, our linear graph is evidenced through 1 over NO2, or NO2 concentration, which tells us that, explain how the graph indicates that the reaction is second order. Okay, so what we would say is, for answering part A, that the second graph of time versus 1 over concentration of NO2, okay, is linear, indicating second order reaction. All right. Write the rate law for the decomposition of NO2. So when we look at this, what we know is that they only have one reactant. And we've determined the order of our single reactant. We've determined that the reaction is second order. And since there's only one reactant, that must mean that the reactant present in this reaction is second order. And so therefore, we would write the rate law is equal to some constant, rate constant K, times the concentration of the single reactant NO2 raised to the second order. Consider two possible mechanisms for the decomposition reaction. So while we have the overall reaction written above, here is the multi-step sequence that it actually is theoretically occurring through. Is the rate law described by the mechanism 1, all right, which was given to us up above? Okay. Oh, sorry. Oh my goodness, my eyesight given to us down below. Sorry. Is the rate law described by mechanism 1 shown below consistent with the rate law you just wrote in part B? Okay. Justify your answer. So remember, the AP will not mark you off for a subsequent part of an FRQ if you got the first part that you're depending on wrong. So what it would do is would mark you off for B, but if you were to answer part C correctly according to your B answer, you should still get the point. But I'm giving you the right answer for B. So would this be the same? And what we look at is based on the mechanism 1 being our slow, we would write that the rate law for the overall reaction determined by the rate determining step, our slow step, step 1, is equal to some value of K times NO2 squared, okay? Because there's two NO2s. I could have written it as NO2 times NO2 concentration, and with raised to their coefficients, because remember with elementary steps, we say that the reactant order for a respective reactant is its coefficient, is the molar ratio in front, which would simplify down to K times NO2 to the squared. And what we would say is yes, mechanism 1 rate law is consistent, okay, with our answer in part B. Okay. As step 1 is the rate determining step. And displays a second order reaction. Okay. Or yeah, a second order reaction with respect to NO2. Okay. Part II of part C is the rate law described by mechanism 2 below consistent with the rate law you just wrote in part B above. And so what we look here is slow. We would write that the rate law for our slow step, which would represent the overall reaction, is equal to K times N2O4 raised to the power of its coefficient for an elementary step, which is 1. Now, before you immediately go right off, oh no, definitely not. Okay, don't forget what you're noticing here is our reactant is an intermediate. So what we're gonna have to do is this is where when we have a slow second step, we need to use that K equilibrium substitution. So what we would need to do is say, well, how can I write the rate law in terms of a non-intermediate? So I look to the previous step and I say, well, according to my KEQ expression of products, concentration raised to the respective power all over reactant concentration raised to this respective power. All right. my KEQ, which is, by the way, just a constant, it's just some type of constant number. It's going to end up being like some number, okay, is going to be equal to, for step 1, where we do see our intermediate, okay, as now a product, we would say that N2O4 concentration raised to the power of 1, because that's the coefficient, divided by NO2 times NO2, raised each to the power of 1. If we manipulate the equation around, we would say then that the concentration of N2O4 is equal to some constant KEQ, right, times NO2 squared. I'm going to simplify it. So then what we do is we take N2O4, and in our rate law, we sub in, okay, our equivalent. So we say then that the rate law is equal to some constant K times big K EQ, which is also another constant, times the replacement for N2O4 is KEQ times NO2 squared. And if we recognize that these are both just constants, we can just kind of simplify this all the way down to some constant K. And so what we get then is, if I bring everything a little closer, we get then that our rate law is indeed equivalent to part B. So upon first glance, you're like, oh no, but when you use our KEQ equilibrium substitution method for a second step rate determining multi-step mechanism, what you'll see is that when we replace the intermediate, we still are able to find that, 1, we can put our rate law in terms of reactants that are part of our overall equation and not going to be just consumed. But 2, we also see that we now can put it in terms of the reactants that match our overall reaction. And we see that being consistent with part B. So what we would say is yes, okay. The mechanism 2, okay, has a rate law consistent with part B, as the KEQ substitution of intermediate N2O4 results in a rate law of a second order rate law. With respect to NO2. Okay, so that's all you have. Hopefully it's nice and short and brief, and good luck on studying for the Unit 4 or 5 test, guys. Bye.